When we say data, we simply mean recorded information. In biostatistics, data often come from experiments, surveys, clinical trials, or field studies. But to analyze data properly, you first need to ask, what kind of data am I working with? Let's break it down. At the most basic level, data fall into two broad types, categorical and numerical. Categorical data describe qualities or characteristics. These are labels or groups like blood type, species of tree, or vaccination status. You can count how many of each category you have, but it doesn't make sense to calculate an average blood type. Numerical data describe quantities, things you can measure or count. Examples include height, weight, temperature, or the number of bacteria on a petri dish. You can add, subtract, and compute averages with numerical data. Let's see some real-world examples. Here's a bar chart of categorical data, showing the number of people with each blood type in a sample. Notice how the x-axis lists categories A, B, AB, and O, and the y-axis shows how many people fall into each group. This is typical of how we display categorical data. Now here's a histogram of numerical data, showing the distribution of tree heights in a forest. In this case, the x-axis shows numerical ranges of height, and the y-axis shows how many trees fall into each range. This tells us not just how many trees there are, but something about the overall pattern and spread of the data. Now let's go a step deeper. Data can also be classified by level of measurement, which affects what kinds of mathematical and statistical operations make sense. There are 4 levels of measurement: nominal, ordinal, interval, and ratio. Let's take them one at a time, with examples you might encounter in biology, health, or environmental science. First, the nominal level. Nominal data are categories with no natural order. Examples include eye color, blood type, or species of fish. You can label and count these categories, but you can't meaningfully say that one blood type is greater than another. Nominal equals names. That's an easy way to remember it. Next, the ordinal level. Ordinal data have categories that do have an order, but the gaps between categories aren't necessarily equal. Think of pain ratings: none, mild, moderate, severe, or cancer stages: stage 1, 2, 3, 4. We can say stage 4 is more advanced than stage I, but we can't say it's exactly 4 times worse. The differences between stages aren't precisely measured. Ordinal equals order matters, but the spacing is unknown or uneven. At the interval level, the data are numerical, and the differences between values are meaningful and consistent. A good example is temperature in degrees Celsius. The difference between 20 degrees Celsius and 30 degrees Celsius is the same as between 30 degrees Celsius and 40 degrees Celsius, a 10-degree change. But here's the catch: there is no true zero. 0 degrees Celsius does not mean no temperature. It's just a point on the scale. Because of this, we can calculate differences, but we can't say one temperature is twice another. Finally, the ratio level. Ratio data are like interval data, but they have a true zero. Examples include height, weight, heart rate, and counts of things. If a tree is 0 meters tall, it truly has no height. And a tree that's 10 meters tall is exactly twice as tall as one that's 5 meters tall. With ratio data, all arithmetic operations, adding, subtracting, multiplying, dividing, are meaningful. Here's a quick summary. Nominal, names or categories, blood type, species. Ordinal, ordered categories, cancer stage, pain level. Interval, consistent differences, no true zero, temperature in degree C. Ratio, consistent differences, true zero, height, weight, heart rate. Knowing your data's level of measurement is critical because it determines what graphs you can create, what statistics you can calculate, and what conclusions you can draw. So the next time you collect or see data, stop and ask yourself, what kind of data is this? What level of measurement am I working with? That's step 1 in being a good biostatistician or a good scientist in general. In the next section, we'll start learning how to describe and visualize data, so stay tuned.